Welcome to Curium. As part of Tool 1 experimental techniques, one of the techniques which you are expected to be able to apply is that of knowledge around an acid base and a redox titration. So the focus of this video is to investigate the amount of a substance which is present in a sample using the backed titration method. Note that this can be called back titration, reverse titration, or double titration. Before you begin, it will be helpful for you to understand how to calculate concentration using the formula N is equal to Z multiplied by V, which is assessed under structure 1.4.5. How to write a chemical equation for the reaction between an acid and a metal oxide or metal hydroxide, and an equation for an acid and a metal carbonate or hydrogen carbonate. This is assessed under reactivity 3.1.4. Understand that coefficients in any chemical equation represent the mole ratio. One of the things students struggle with is why would you do a more complicated backed titration when you could just do a regular titration? And the answer is you wouldn't. You only do a backed titration if a simple titration will not be able to get you results. An example of this is maybe where you're starting with a solid and I can't dissolve that solid in water, and I have to dissolve it in something else instead. Or maybe there just isn't a very clear color change or endpoint possible for this reaction. So for example, if you have a very weak acid. Or maybe you just don't have a suitable indicator at all. So you only do a backed titration if you can't do a regular titration. All back titrations will follow similar steps. You'll start with a chemical, for example, X. And the problem with X, maybe you don't know its concentration. Maybe this is what you're trying to determine. The first thing you will do is dissolve it in another solution, Y. The key thing about Y is it has to be in excess. Because what you want to happen is for some of the moles of Y to be used up, but not all of them. So you make sure that when you add it to solution Y that you've so much of Y that it uses up some of Y, but not all. And then you do a second reaction. And the point of the second reaction is to figure out how much of Y didn't get used up, so how much of it was left over. Because if we know how much of Y we started with, because we know what we put in originally, and we know how much of Y was left over, because we'll figure that out from our second reaction, the difference between them must be what reacted with X. I think it makes it a little bit easier to understand when you see an actual back titration being done with example species that could be used. So let's say if you started with a solution of ammonium nitrate, and the problem here is you don't know the concentration. What you would do is react it with an excess of something else, say for example NaOH. And I know when that happens, some of the NaOH is going to be used up, not all of it, because we said it has to be in excess. So some of your NaOH gets used up. To figure out how much of it doesn't get used up or how much is left over, I carry out a titration. So I would just get something that the NaOH reacts with, like the HCl, and I know that I can read off the burette how many moles of HCl is required to neutralize the leftover NaOH. Because if I know how much NaOH I initially put in, because I was making sure that it was in excess, and I know how much was left over, because I know that from my titration, then I can work out how much of it reacted with the ammonium nitrate, because my number of moles of sodium hydroxide will be equal to my number of moles of ammonium nitrate. Back titration calculations will all follow a pretty similar process, where initially you'll have been given a mass or a volume of something, and that something will be either impure or has some kind of an unknown concentration. For this example, let's just use the weak acid as our something, because it will make it a little bit easier to explain. So your steps will be as follows. You'll add your acid or something to something that it reacts with, so maybe a strong base, and you make sure that that strong base was in excess. Remember that you know the moles of the base when you're starting. Once they react, some of the moles of that base are going to be used up, so you're going to want to figure out how many moles. So to figure out how many moles, you titrate the remainder with something it reacts with, like maybe an acid. And remember, with that acid, you'll know the concentration and you'll know the volume because you'll read it off the burette in your titration. So now you essentially know the number of moles which are left over in the strong base because you link it to the titration. And you'll know how many moles you put in originally because you made sure they were in excess. So By linking those two numbers together, you can figure out how many moles of acid were required to react with your something. A very typical experiment which uses this concept of a back titration at DP is that involving eggshells, where you're trying to determine how much of an eggshell is actually calcium carbonate. So the first thing you do is you start with a particular mass of eggshell and you crush it up with a mortar and pestle. With that eggshell that's now powder, you add that to an excess acid. It's going to react with some of that acid, but not all of it. So to figure out how much is left over, you carry out a titration. Let's look at how we could process the data collected from this experiment. You start with some crushed eggshell, which is now a powder. You add that to the excess HCl, knowing that it will use up some of that HCl. To determine how much HCl is left over, you carry out a titration. That HCl will react with NaOH. Based on the burette, I can read what volume of NaOH is required to neutralize the HCl. Using that volume and the given concentration of NaOH, I can now calculate the number of moles of NaOH, and because they have a 1:1 mole ratio in a chemical equation, I know that that's also equal to my number of moles of HCl. So if I know my leftover HCl based on the titration, and I know how much HCl I initially put in, I know my initial HCl, that means the difference between those two values must simply be what reacted with the eggshell. I'm now going to make an assumption. I'm going to assume that in that eggshell, CaCO3 is the only thing that would react with a HCl. So I assume that my number of moles of HCl that reacts with the eggshell, that eggshell CaCO3, I can link that as the number of moles based on the mole ratio in that chemical equation. Now that I know my number of moles of CaCO3, I can simply convert that into a mass of CaCO3 and represent it then as a percentage purity. So I know whatever initial mass of eggshell I put in, I know how much of that is actually calcium carbonate. Now let's look at a very typical example of a medium level exam question. This question in total is worth 11 marks, so should take about 16 and a half or 17 minutes. If you want, you can pause this video now, or if you want to stick with me, I'm going to talk through how you come up with the answers to this. The question tells you that the percentage by mass of calcium carbonate in eggshell was determined by adding excess hydrochloric acid to ensure that all of the calcium carbonate had reacted, and then your excess acid left was titrated with aqueous sodium hydroxide. One thing to note before we begin, the question says the word excess. You can probably assume that if the word excess is there, that what you're dealing with is a backed titration. So what they've told you is that they have an eggshell, and that eggshell, some of it is calcium carbonate. They don't know exactly how much, and they want you to figure out how much. And they want you to represent that number as a percentage. So the focus of this experiment is how much of an eggshell is actually calcium carbonate, what percentage of it. So they first got that eggshell and they added it to excess hydrochloric acid. How much hydrochloric acid? They added it to 27.20 centimeters cubed of this concentration. Note that the first thing I'm doing is changing those volumes into decimeters cubed. You can assume that you're always going to have to do this. So once you have the volume turned into decimeters cubed and you can use the concentration, you can use that to work out the number of moles. So what I now know is the number of moles of HCl which was required in order to react with the eggshell. That eggshell that I put in was 0.188 grams. Note that this is the mass of eggshell, but it is not the mass of calcium carbonate. Only some of that 0.188 grams of eggshell will actually be calcium carbonate. So they're not the same thing. That's a common mistake that students make. Okay, now I know how many moles in total of HCl I've put in. I know that not all of those moles will have been used up reacting with the CaCO3. Some of them will be left over. And how I figure out what's left over is I react them with NaOH. How much NaOH is required depends on the values I get from the titration. So again, I have a volume that I will turn into decimeters cubed, and I know the concentration of the NaOH as well. So now I know the number of moles of NaOH required for neutralization is the same as the number of moles of acid. So I know my number of moles of acid which is required to neutralize. So think about the numbers that I have now. From part A, I have the total number of moles of HCl that I added. From part B, I have the number of moles that was left over. The difference between those two numbers is the value that I can use when I'm asked to determine the amount of HCl that reacted with the calcium carbonate in the eggshell. So the difference between those two numbers. So I know that my total moles I put in was 0.0544, and I know my number of moles that was left over. And now I also know how much HCl was required to react with the CaCO3. The next part of the question asks you to state the equation. So the reaction, one of the reactions that's happening is between HCl and the calcium carbonate in the eggshell. Because what's reacting is an acid and a metal carbonate, it's always going to form a water, carbon dioxide, and the salt. So my acid is HCl, my metal carbonate is CaCO3, that's easy enough. Water and carbon dioxide, again, pretty easy. My salt is CaCl2. Make sure to take a second and form this correctly, as without it formed correctly, you won't balance it correctly. And this is a 2-mark question, which means that one of the marks will be going for correct reactants and products, and one of the marks will be going for balancing it correctly. So now what I know from this equation is that for every 2 moles of HCl I have, they react with 1 mole of CaCO3. So if I know that 0.00306 moles of HCl react with CaCO3, and I know that from part C, I know that half that number of moles will be of CaCO3 is what was required for that reaction. So I simply divide the number by 2. How did I know it's a half? I just linked it back to the chemical equation, and it's in a 2:1 mole ratio. So now what I know is that of that eggshell, 0.00153 moles of it is calcium carbonate. So what I want to do is turn that into a mass, because then I can compare the mass of calcium carbonate to the mass of eggshell. Right now, I can't really compare the moles of calcium carbonate to a mass of eggshell. So what I do is I turn that number into a mass. And that's pretty easy for me to do. I just get the molar masses of each of the elements from the periodic table: calcium, a carbon, 3 oxygens, and that works out at being 100.09 grams per mole. So I know that if I have 0.00153 moles of calcium carbonate, that is 0.153 grams of calcium carbonate. And I also know what I originally put in. I started with 0.188 grams of the shell. And now I know how much calcium carbonate it is. So that's easy for me to turn it into a percentage. So what I've now figured out is that of the 0.188 grams of shell that I put in, 81.4% of it is calcium carbonate. I had to make some assumptions in coming to this conclusion though. I was assuming that the eggshell has calcium carbonate in it and that nothing else that's present could be participating in this reaction, because my whole idea is based on that the acid is reacting with calcium carbonate. But there could be other things present as well. I'm choosing to believe that they're not, or I'm assuming that they're not. And that's my major assumption here, that only CaCO3 is reacting with the acid, or that if my other impurities that are there, that they're inert or that they're not reacting with the acid.